Just.
So my talk will be mostly, of course, about optimization phenomena. It will be related to statistics at some point. And I was trying to make it like light on theory, on optimization theory, but if something is not clear, please don't hesitate to interrupt me. So you see my slides, right? Everything fine?
Yes, it's okay.
Okay, so let's proceed this then. So my talk will consist of two parts. First, I will talk about implicit bias in general optimization algorithms. And in the second part, I will talk more about the research I did with my PhD students, Alexander Posch. So first, let's discuss in general what we call implicit bias in algorithms. We start from supervised learning, where the task is given some data. You have some vectors A1, A2, AN, and to each object there is a label B1, B2, Bn. It can be plus or minus 1, or it can be just arbitrary real number. And our goal is to discover some rule, which is a function, right, that takes these objects as an input and outputs as a label or approximates the label. So that's what we would like to find the rule, and that's what machine learning does, right? We would like to discover this rule. Why do we need to discover this rule? Because together with labeled data, of course, we have some unlabeled data. And if we kind of sure that we discover a good rule, we would be able automatically to label all this data, to classify it, et cetera, et cetera. And how usually we do this? So we need to first consider some class of functions, right? Otherwise, it's untractable task. So let's say, for instance, we can take h as a linear function, or we can take h as a polynomial function, or we can take h as a whatever neural network. So here x means, if it's a neural network, it means all the unknown parameters of neural network. If it's polynomials, then all coefficients of the polynomial, etc. And then we need to choose a loss function, which means that b is our given label, and b hat is a label that we found from the model. And we would like, of course, to, if they're close to each other, b hat and b, then maybe loss function is 0. If not, we should get some penalty for this. So, and our goal, of course, is to make a loss function as small as possible across the whole data set. So for instance, here we take loss as a very classical one, the quadratic loss. And then we consider the total loss across the data set, which means we just minimize the sum for each object AI. So I hope this is clear. This is very standard both in statistics, in machine learning, in optimization, and basically the main problem, let's say, of modern machine learning. Okay, any questions? Good. So let's say we have some data, and we need to find a good function that describes this data, this H rule. So how we can proceed? Let's say we restrict ourselves to polynomials. And if we restrict ourselves to polynomials, what we can do? We can take the simplest polynomial of the degree 1, and that would be the best approximation we can get, which, as you see from the picture, is pretty poor. We can consider polynomial of degree 20. And the polynomial of degree 20 will basically learn every single point there. So it's indeed polynomial. It's just because of scaling, it looks like it's piecewise smooth, but it is a polynomial of degree 20. And so both, in the first case, we call it underfitting. All right, somehow we use very few parameters, and because of this, our model is very poor. We cannot learn our data set actually well. In the second case, overfitting, we use too many parameters, and because of that, we basically went through each individual point, but our model won't be generalized well for the next points. And most likely, if you look at the picture, you would think that the best model would be like just a quadratic polynomial. We cannot do perfect. We don't need to do perfect, but somehow it really represents our data in the best way. So this is like a difference between underfitting and overfit. And this was like a very standard paradigm for the classical statistics, classical machine learning. But let's see what we have nowadays. So overfitting is more parameters than data. In the same time, neural networks, they use many parameters, but somehow they still predict extremely well. So it's not very clear what's going on. At the same, and also additional to this, so this our main minimization problem, right? The total loss problem. Usually this problem has many solutions. And somehow, if you use neural networks or other modern methods, not every solution is good for practice, for generalization. But somehow, neural networks or other models, they discover the good solution pretty often. So in optimization, we have this question is like, why they choose good solution and not bad solution? What are the properties? Because the algorithm is the same. We just can change maybe initial point, maybe learning rate or step size, etc. There are not so many things to change. And somehow they converge to good and not bad. So, and in the last 10, 15 years, this phenomena has appeared that is called implicit bias, which is basically, roughly speaking, is a tendency of an algorithm to converge to one solution and not to another. So somehow something that we don't have control over, or at least very little control over, and the algorithm is smart enough to choose the solution we want. So that's what we are going to talk, and now I will illustrate how different algorithms have different implicit bias. Okay. So let's start from linear regression. This is probably the example of implicit bias that you're mostly all familiar with. So linear regression means that we have a linear function h and a quadratic loss. We can call it least squares, linear system, whatever, which is of course this problem. And if we so let's suppose that we have a matrix n by d with less rows than columns. And of course, usually if you don't assume anything else, then this system would have infinitely many solutions. So on the picture, you have one hyperplane, another hyperplane, they intersect on another hyperplane, and there are like many solutions, right? The all red line is the solutions. And we want to run gradient descent, which in this case, we'll have the representation as on the slide. And so, of course, we will, if the step size alpha is chosen small enough, we will converge to a solution. But what is interesting is that we converge not just to a solution, but we will converge to a very specific solution. We converge to x star, that is a projection, orthogonal projection of x0 onto the solution set, which is kind of a very reasonable, but also very nice property, right? There are many solutions, and somehow gradient descent converges to the closest one, closest points from which we have started, which is kind of a nice property. So in this case, this is an implicit bias. So I hope it's clear what I meant by implicit bias. So let's go to another. Any questions? I'm sorry because I cannot see participants and I cannot see raised hands. So
these locations are known exactly in your problems. There may be another uncertainty with xi's. Xi's could be observed with errors. The input xi's could be observed with errors as well.
Not sure what
A matrix can be observed.
So here it's exact matrix. It's exact matrix that has a solution.
Yurii, let me explain. I think I understand what Professor Kukush is asking. So you don't have any uncertainty or noise. Let's say going ahead, you have two clouds you separate by logistic regression. You could have many lines. What Professor Kukush is asking, in terms of interpretation and practical, how we know that we prefer one solution to another. So problem with your implicit bias, I mean, just generally in that literature, that it's not clear implicit bias towards what? What is kind of after regularization, what we use for regularization? What would be our goal? Like for, let's say for SVM, Vapnik, he has nice result that it would be kind of minimizing that risk, and he can find it. You, with your technique, could find maybe other solutions with some iterative. So it's just general for implicit bias. How we have to interpret it if we go away from pure least squares
So
linear problem.
Okay,
Does it make sense?
I will consider other problems that it's not only linear regression, not least squares. I will talk later about logistic regression as well. Maybe it will be clear. So implicit bias is not about practice, or it's more about, it's only like a property of an algorithm to converge to one solution and not to another. And it's not clear what properties this solution has. We have to study this in details. Different algorithms on different problems have different implicit bias. So it's not about, it's like it's already carved in stone and this is the rule. It's only like we need to find the name to call this property of the algorithm to prefer one solution and not another.
So
people started.
You do not know even if it's let's say if it's acceptable. It's another problem. Like for let's say logistic regression, you can separate by many hyperplanes often completely separable if you use that assumption. So your convergence, you do not know even if it's acceptable for a complete separation. You would prove it later with your convergence.
So for logistic regression, I have very, I think, right slide for your question. So I will talk in 3-4 slides about logistic regression specifically. So this is a linear regression. Let's not jump over it. It's a very simple one. And I think it's clear that among all solutions, X star is the best solution kind of for us, because there is no more information, right? We just only have these hyperplanes. And of course, it's the most reasonable thing to converge to the solution that is the closest to our initial point. Right? In some sense, it's a very L2. It's a problem in L2 metric. So it's very reasonable to be close in L2 metric. If we wanted something else, probably we would formulate our problem not in L2 norm, but in some other norm, and maybe we would get something else. But for now, I think it's very reasonable to assume that, yeah, it's a good property to have in mind. Of course, it's very intuitive. It's like there is nothing to prove here. It's very obvious and it's very well known.
But there is the main assumption that you're starting from that x0. It's something that is embedded in your problem. If you start from another x1, or it would be some problem later that x0 is quite close to that line, almost like zero in some sense, then convergence probably would be also problematic. Okay, sorry, just trying to understand.
No, that's fine. One more question. Yep. And orthogonal regression, is it covered by your methods?
I don't think. First of all, it's not my method. It's a standard result. I don't give the authorship here because it's so standard that I don't even know who was the first to notice this. Honestly, I don't know what is orthogonal regression. What do you mean?
When you just project, you draw a straight line and project your observation on your line, and you want to minimize the length of this perpendicular.
But I don't know the set. So the set red, I don't know. It's not given to me. So I only have the blue and the like yellow kind of hyperplanes. Right?
He has just a matrix. He doesn't have exactly kind of linear algebras. So it's not orthogonal. It's just least squares. Traditional problem, but with nothing special here, I believe.
Exactly.
I believe Professor Kukush means that often we don't know what kind of variables to choose y and x and least squares, and there are some regressions defining depending on what y, what is x. Okay.
Okay.
Yeah, I think Professor, you
Okay. Okay, so I hope it's clear with linear regression. We can always come back later if it's not clear, so no worries. Let's move to another example. Now let's consider alternative projection. So we are given two convex closed sets, A and B, and our goal is to find a point in the intersection. And so usually we assume that the set A maybe is simple enough that we can project onto it, maybe B is simple enough that we can project, but even with two simple set, it's actually very hard to project onto intersection. Think even about if you have two balls, like very easy to project on another, but like intersection is like, oh, it's not so trivial, even in like R2, right? There is no kind of analytical formula, or it's not trivial to get one in general. So alternative projection method is basically, okay, we will project first on one set, then we project to another set, and we will iterate it until we converge. So basically here we have a blue line, one set, and a green circle, green ball, another set, and we jump between projecting onto line, and then a ball, etc., etc. And intuitively, of course, we should converge. We should become closer and closer to the intersection.
Why intuitively? Because it's a convex problem in some sense.
Convexity of the set is very important. Otherwise, you cannot even define what is a projection.
No. I understand that, but in terms of, I forgot. In terms of alternating projections, convergence. It's because if we convert into linear, it's least squares with some convexity embedded for convergence.
There are many ways how you can interpret it.
Okay.
You can formulate it as a fixed point theorem and reduce it to
exactly.
Krasnoselski Mann algorithm. You can say that it's a projected gradient method and it converges.
No, Yurii, sorry, because I am Krasnoselski student. That's why I'm trying to go ahead.
Okay. Oh, that's great. So Krasnoselski Mann would be the fastest explanation, basically.
Okay.
So in general, we do converge to the intersection, but in a very specific case, we can say something more about this X bar point. It's not just an arbitrary point in the intersection, but it's a specific point. So in particular, when A and B are linear or like even affine sets, then we converge again, not to arbitrary point, but to the projection of initial point onto this intersection. This is
I remember the work of von Neumann. Yeah, in neural networks they would cite it still. Okay.
Yeah. So again, we can say that basically implicit bias in this case when A and B are affine sets is convergence to the projection of initial point onto this intersection, right? Not an arbitrary point, but kind of the best one, because we want to be the closest maybe to the initial point. And in this case, the algorithm automatically discovers this point.
Okay.
It's a different than from the previous one, but also, right, there is some implicit bias under some assumption when A and B are good sets. Any questions?
So it's guaranteed because of Krasnoselski to convergence for particular x0, it would be particular convergence to some fixed point, only one. If we start from another point, it could go into intersection of A, B to a different point.
Yes.
So we do not know what is the best. The best it would be how we started. Okay.
Somehow, if you start from this point, maybe it's reasonable.
Yes.
Okay.
And this limit is the closest point to x0 from the intersection, right?
So projection is the closest point from x0 to the intersection. Yes. So whenever you say projection here, it's orthogonal projection, yes. The closest one.
Obviously, it would be some it's in some sense it's closest, but you have. I mean, it's not a kind of smooth convex set, right? It could be some problems with the edges, like if you consider intersection.
Yeah, it's not different. Of course, the projection operator is not differentiable, so
exactly. Sorry, I'm like practitioner thinking. I forgot that I used to be mathematician. Okay.
And we can this result can be generalized, and because this one maybe it's like pretty simple stuff, but it can be generalized, and with this generalization we will discover pretty modern things. So that's the same result from the previous one, right? If A and B are affine sets, then this algorithm converges to the projection of x0 onto A and B. And we would like to generalize. This will require some new devices to introduce, but bear with me, it shouldn't be that difficult. So we consider some function h that is from RD to extended real line. And it's a convex function plus some regularity assumptions that I don't want to dig into it for now, but it's differentiable over some domain, etc., etc. And we introduce the Bregman distance. That is basically the first order expansion of Taylor expansion of function h between points x and y. It's not a distance by itself, but we just keep this name by tradition that it's Bregman distance. It's not even symmetric, as you clearly see, but it's because of convexity, it is not negative. So at least this property we have. So, but symmetry is, of course, and triangle inequality, they don't hold. But many optimization algorithms, because in standard Euclidean setting, you have whatever, the most prominent thing is like the norm or L2 norm is present somehow implicitly. So most of them actually will work if you replace this Euclidean norm by the Bregman distance. So that's why it's so prominent. And the idea of this generalization is you introduce a function h that plays nicely with the geometry of your problem. So maybe you know something extra about your problem, and for this particular problem, you need to play with the function h that you introduce. So for instance, we can introduce now Bregman projection, not Euclidean projection before, but a Bregman projection, and we will use a capital P letter. That is minimizes as not a Euclidean distance, but a Bregman distance. It's a convex problem, as before.
Yurii, I just want to interrupt because I don't know when I have to take off, but because it's a probability and statistics seminar, I want to say for Kiev's audience that there is a nice page Krasnoselsky and Crane, where they studied such techniques when x0 has Gaussian distribution, and then how to handle it with arrows. But it just that it has also some probabilistic analysis. Okay, sorry.
Yeah, and so. For instance, if h we consider as a square norm, Euclidean, like L2 norm, of course, whenever I don't say it, it's always L2 norm, then the Bregman distance will be just a normal distance as we get used to, and the Bregman projection will become the normal orthogonal projection. If instead we consider h as entropy, so it's x log x if x in the simplex and plus infinity otherwise, or negative entropy, then the Bregman distance becomes, it's called Kullback-Leiber divergence. It's like very prominent in statistics and has this formula.
Wait a second. It's something, by the way, I just kind of it bothered me that you now I see that it's Kullback-Leiber divergence, or according to Krasnoselsky, he would use so-called Hilbert-Birkhoff metrics for convergence for positive systems. And here, what I'm trying to understand, Yurii, that like practitioner, when you have your algorithm and it would, if you don't have stopping rule, even when you are inside intersection of A and B, you could make some iterations, or you could always find like on the border projection on that set. Doesn't make sense what I'm asking.
I thought that we are mathematicians here, not practitioners. So I thought that we shouldn't care about these details. Of course, at some point we should stop the algorithm, and this is not probably, I think it depends on the problem, on the, I don't know, the purpose of the problem you solve, when to stop. There are many things how you just measure the distance, of course, from x0 to the both sets, and based on some epsilon, you stop it, etc.
Okay.
So we are still in all the talk. We only care about theoretical statements. We will talk about convergence rate. So it's important to know how many iterations you need to go. So there will be some bounds about the rate. So you can have some rates here. Of course, it's not just convergence. It's not asymptotic convergence. There are precise rates. Sometimes all constants are known. Sometimes not. But still, I'm not going to discuss when we should stop. It's more about. Okay.
So you're not discussing like regularization according to stopping rules. Okay.
No stopping rules.
Okay.
Okay. So this is for this age. These like two most prominent examples, right? One is Euclidean, another is Kullback-Leibler divergence. So when H is entropy, and the same result will hold. So if A and B are affine sets, and now we use not a Euclidean projection, but this generic Bregman projection, we still have the same result that we converge to the projection of x0 onto this intersection. So, which is kind of interesting because it seems like it's not about the orthogonal projection. There is something more important, more general thing about the statement that we have seen before. And this last statement actually leads to very nice results that people use basically daily nowadays. That is called synchron algorithm. So I will show us an example of why synchron algorithm works, how it's exactly the instance of the previous framework. So let's say we have a non-negative matrix Y, and we have two vectors R, the row vector, and C column vector with the same sums. And our goal is to find two diagonal matrices, D1, D2. So the matrix X, that is basically the multiplication of D1, Y, D2, has margins R and C. Margins R and C means that the row sum of X is R and the column sum of X is C. So in formulas, it will be like this. This is our problem. For now, we skip why we care about this problem. But it's an interesting problem because you see constraints are very linear here. At the same time, the objective is very nonlinear, right? It's something about multiplication.
So what is X? What X we are trying to find by consider that linear transformation with D1, D2? What is, I cannot see non-negative, it's great. It would transform positive con into con. But what is D1, D2 matrices? What is the meaning of that?
So for statistics, it's actually very standard thing. So if you have contingency table and you would like to, so you have some margins and you would like to preserve the ratio between entries, right? But you need to kind of extend your table to, because I don't know, the full distribution. You have a sample of some small data set, but then you have full population, and you want to understand, okay, how actually many people smoke.
Okay.
So for instance, for this task, I will talk about this later. It's not super important. For now, let's say just theoretical problem. And it's interesting because we have two. So if matrices are n by n, it means we have n unknown in D1, n unknown in D2, so two n unknowns. But we also have two n kind of constraints, n constraints here and n constraints there.
And D1, D2 also non-negative, right?
Of course, yes. Same as
Okay, makes sense.
So it's like we have two n constraints, linear. We have two n variables, unknown variables. But at the same time, it's very multiplicative objective and very linear constraint. So it's not clear how to solve it. But the algorithm actually that solves it is as follows. We start from x0 matrix, and we initialize it as our matrix Y. And then in turn, we normalize first columns, then rows, then columns, then rows. By normalization, I mean, it's very hard to satisfy both constraints, either this or that, but it's very easy to satisfy one of them. So it's very easy to make the column sum as a C. But when you satisfy column sum as C, of course, you ruin your rows. So now you switch back and you start to normalize your rows. And you jump between these two processes. And in the end, you converge to the matrix X that will have these margins R and C. Is this clear?
Yeah. It's just I forgot. It's not metropole. How it's called that algorithm when you go by margins and switch both and forth in, and then you convergence of this algorithm. It's actually a good exercise for students, right? And the idea probably of proof is still what statisticians they call callback that metrics, right? You metrics between arrays. Am I right?
So yes, exactly. We can actually reformulate this problem as minimizing KL Kullback-Leibler divergence between X and Y, such that X belongs to the set A and B, where A is your row constraint and B is your column constraint. Maybe it's not immediately clear, of course, but like let's say this is you write formula for KL. You have linear constraints, so you write optimality condition, which means like just Lagrangian. You write it down, and you immediately so it's like 3 lines of proof, and you immediately get that okay, X must be of this form. So this is your like Lagrange multipliers, roughly speaking, D1 and D2.
And what is written here in denominator? We have a vector.
Yeah. So
one vector is divided by another vector.
Yeah. So it means it's coordinate wise, and this is a Hadamard like product. So it means each column has to be multiplied by a corresponding number.
No. I believe Professor Kukush meant you didn't put transpose in the number 3, but X trans T times 1. It's just a number, Professor Kukush.
Yeah, but
no.
And X,
C is a vector, and X1 is also the vector. So you divide one vector over another, which means you divide it like
by components.
Component-wise, yes.
Yes,
and then each column is multiplied by this number again, correspondingly.
Yeah.
I didn't want to be like super rigorous because then the formula would be just unmanageable. But I hope intuitively it's clear what it means to normalize columns and what it means to normalize rows. So the formula by itself is not so important. Okay, so what's interesting is that this problem, the first one, is equivalent to problem 2, minimizing KL subject to this constraint A and B. And of course, now you won't be surprised that like normalizing columns is nothing else as it's a KL projection of xk onto B, and normalizing rows it's KL projection of xk tilde onto A. So we are exactly in the settings of the previous algorithms because A and B are 2 affine sets, and this is an alternated projection algorithm. So of course we should converge to the projection of our initial point onto the set intersection of A and B. Our initial point is Y. So that's why we indeed solve this problem too. So this algorithm is called synchron algorithm. It's very important nowadays in optimal transport. So I didn't formulate it as an optimal transport problem. The problem I consider is called matrix scaling problem. So this D1 and D2 are called scaling, and that's why so it's prominent, but in statistics, it's known as the Deming-Stefan algorithm, in particular for considering contingency tables. And basically. And the reason we have convergence exactly because it's alternated projection method. And Dr. Fomenko mentioned just before that it's about Hilbert metric, etc. And indeed, in order to get a rate for this method, which is a linear rate, you can study because it's a contraction actually algorithm. So in order to study this contractive factor, indeed you can reformulate it in a Hilbert metric with like Birkhoff stuff, etc. And then you get a nice rate for this method. But it's more advanced thing. But so the approach we study, it doesn't give us a rate, but it gives us proof of conversion to this particular solution. Okay, any questions? Good, then let's go for, okay, if you write me something in the chat, why not to postpone the discussion, listen to the lecture first? I think it's, I don't like to have a long discussion, I agree, but I think it's very helpful to have questions from time to time, because otherwise maybe you miss something and then you cannot understand further stuff.
Yeah, I want to apologize. I don't want to hijack it. Just I wrote to Professor Kukush. I have to take off soon, so I just made some comments. Okay, thank you.
Yeah, no worries. Okay, now the logistic regression. So let's say we have a data set that consists of, again, vectors A and the labels, let's say, positive and negative, or +1, -1. In this case, it's a linearly separable data set. It doesn't need to be, but we consider this case when the data is linearly separable. So we consider a linear model. So we would like to separate them with a hyperplane. And of course, in this particular case, you see there are many possible ways how you can classify the data. So this one is good, this one is good, this one is also. But like probably among these three, I would claim that the third one, the red one, is the best because somehow it has the widest margins, right? With the blue data set and with the green data set. So among all these possible data lines, we would like to find the red one. That's kind of the best. Okay. So for logistic regression, we consider the following laws. The idea is, so it's logarithm of this stuff. The idea is that if B hat and B have the same sign, then this is positive. With minus, it's minus. So this log becomes kind of small number, right? It cannot be 0, but it can be like arbitrarily close to 0. And vice versa, if they're of opposite sign, then this would be negative is minus, it's positive. So then the loss becomes large one. So the idea is to have B hat and B of the same sign. And of course, we minimize it across the whole data set. Okay, so this is our function f. And let's say we run gradient descent. So with some step size alpha, right? We don't need to run the formula. And so logistic regression is a very good approach, not only when the data is linear separable. It's actually much better when the data is not linear separable. But it's kind of interesting to see what happens with logistic regression when the data is linear separable. Because of this, it's easy to see that there is this vector x. If there is a vector that separates data, it means we can always find x that has an inner product with every AI of the same sign, either +1 or -1. And then with BI, which is also plus or minus, we can always make it like as small as possible. Right? So these two classes of classes of objects, we will find x that makes this like just this number is just positive. So e to the with minus positive will be like close to 0. And of course, if x works, then we can multiply x by 10, by 100, by 1000, and make it smaller and smaller and smaller. So because of that, it's clear that we can make function, because it's kind of gradient descent, what it does. It makes the function value smaller and smaller and smaller, but it cannot make it 0 because 0 is an infimum, it's not attainable. And somehow, since basically we don't converge to the we never attain the infimum, the iterates must go to infinity, because otherwise there will be also a limit point, and by continuity you should converge. So we don't converge, the iterates become unbounded in this case, they go to infinity. But somehow, who cares about the iterates? The function value still decrease. So somehow this is a very different situation from the previous algorithms, right? In the previous algorithms, we always had convergence, and not only convergence, the iterates told us something more. Here, the iterates don't tell us, like at the first glance, they don't tell us much because they diverge. At the same time, we do have implicit bias, which is very interesting in this case. So if you use normalized iterates, xt over normal xt, then they converge to a vector that basically define this red line. It's like a normal vector that defines this red.
I'm confused. So xt, what does it mean xt tends to infinity? If you simply use...
It's a shortcut to mean that xt is the norm of xt goes to infinity. So it's like basically unbounded sequence.
But why it's unbounded? Wait a second. Like standard techniques, it's like to use Fisher or Kantarovich to fix gradient descent. to some constant after many iterations. So
no, let's say because if xt was bounded, then we can always select the convergence subsequence. If you have a convergence subsequence, there should be a limit, but then like the function values would also converge to a concrete point. But if it's like, think about exponent, right? The exponent.
Exactly.
It can become smaller and smaller and smaller and smaller value. And of course, in order to kind of to reach this infimum that we never can reach, but we're like trying and trying.
You have to stop.
Iterates go to infinity, basically. The same happens here, just because of the same kind of thing. So this is only because the data is linearly separable. But even in this case, the data is linearly separable, still no problem. Still, the normalized iterates converge to the best possible hyperplane, which is like pretty interesting thing. There are many ways how they could converge, but among them, they choose this best separated one. And here is like, actually, it's not about x0, not about initial point, not about the parameter alpha. It's just the property of the algorithm by itself. That was basically, you remember you asked me something about logistic regression, so maybe now it's a bit clear how this related to logistic regression.
By the way, if we assume that it's just two Gaussian clouds in some sense separable, there is technique called discriminant analysis or something people they often like to use instead of logistic regression. How it would work, or you've never even
no idea.
Okay, sorry.
Yep. Okay, any questions? Good. So, okay, now let's go to linear regression again. So we have the same problems that we have seen. And now let's do something strange. Let's do this change of variable. Instead of nice variable x, let's inject some nonlinearity. So instead of x, we will consider u squared. Again, everything is like element-wise. So each coordinate is raised to the power 2. Actually, this is, you may think that it's actually not good because the problem with x can be positive and negative, but when we have u squared, it becomes just positive or just a negative. So let's do slightly even more complicated. Let's do u squared minus v squared. So then problem 1 star and problem 2 star, they're equivalent. Of course, problem 2 star looks like much harder, right? Like who on earth would do this? You can think about.
Yurii, and if audience allowed, I wrote it to Professor Kukush. Actually, it looks confusing for mathematicians, but Krasnosel's he considered it as one of his big innovations. He calls it method of functionalization of parameters. When you have implicit bias in linear system, let's say, what does it mean? You have multiple fixed points. So you consider some functional to get just only one fixed point. And that nonlinear function, it makes problem more complicated because it's nonlinear now problem. But in reality, you can use gradient descent, Newton-Kantorovich, all techniques. It's sorry, I have to go, but it's how I think that it's would be useful for audience that vision of how you describe it, because it looks very complex, right? Okay.
Yep. Thanks. Okay, so now I hope it's clear that if you do this horrible change of variables, this u squared minus v squared, then these problems are equivalent, so we can proceed. Why do we do it? First, it might be interesting. Second is like, we do understand very well how to solve convex problems, but we don't understand very well how to solve non-convex problems. So, and neural networks, let's say, they're notoriously non-convex. So this way, maybe like if we inject non-convexity in a controllable way, maybe somehow we can still handle it and like step by step try to understand how to do this. So this is like, let's say, the second approach. Then we run gradient descent. So gradient descent, again, the formula is not so important, right? But we just differentiate over u and v. We write gradients. And again, this circle means Hadamard multiplication, so element-wise. So that would be the gradient of this objective. And that's exactly what I said before. The first problem is nice. It's the best problem you can think about. The problem 2 is horrible. From the we drop convexity. We don't have. It became much more nonlinear. So very strange to study. At the same time, people notice. At first, I think in practice, people notice that if you use a right initialization, what is right, we will talk later about it, but it has a different implicit bias. So for X, we already studied the implicit bias, but now for U and V, the implicit bias would be that we converge to a sparse solution. By sparse, I put quotes here, so I explain in a moment what I mean here by sparse solution. So by sparse in quotes, I mean the L1 sparse solution. So the solution of this problem. So among all solutions of two linear system, we will find the one that has the smallest L1 norm. It's well known, like, right, from compressed sentence that, like, if you minimize L1 norm under some regularity assumption, it's typical that you discover among all solutions, you discover the sparse one. So in particular, let's say I generated some linear system. So here, if you consider L1 norm solution for X, this in the left, so this is like the true solution, and this is the norm of it. The green one is the one that from solving this problem, minimization of L1 norm. And the red one is if I minimize this gradient descent, the previous problem on the previous side. So this is like what they call U square minus V square solution. It has, of course, it has slightly worse norm, but somehow visually is basically indistinguishable from all the previous solutions. It can be slightly worse, and we can discover also different solutions. So let's say the true solution, by true I mean the ones that I just have to inject it because I need to inject some sparse solutions. But of course, it can discover like even sparse solution in some sense, right? So L1 norm is different, and both are very like similar in this case. So this is the implicit bias. From this moment, I will be talking about, right? So if you use the right initialization, then we will converge to this sparse solution. And one goal is to understand why we converge to this solution, and second is to understand how actually we converge, like under which assumption, and etc. So that's basically the main question we are going to study. And although, right, I said that we can study a general linear system and work with U and V variable, but somehow it's much easier for us to work with a non-negative linear system and just work with the variable U, because we can easily, all the stuff I'm going to tell you, we can easily reduce to just from U variable, we can always generalize this to U and V variable. So from now on, just for simplicity, to have less notation, we will consider a non-negative linear system or non-negative least square problem. So now we do change of variable, x equal U square, and we will have this problem. So we run gradient descent, and that's basically the advantage, right? I only now have to care about one variable U, not U and V square, so it's just faster to write. So this is the update we already seen. Now for U variable, because you have U square in the parentheses, maybe it's reasonable to square this equation, just to have square on all sides. So let's square it. And now let's do change of variables, of course, right? Now U square is, let's be X. So we got this update. So they're basically equivalent. And it's somehow strange, right? We still don't understand why this scheme, this multiplication converges and under which assumption. So under like some strong assumption, people, and when alpha goes basically to 0, so when it's a continuous dynamic, so it's not a discrete algorithm, but a continuous one, people study it and prove something, but there are no kind of practical algorithms that, like, under reasonable assumption, we can say something about convergence of this scheme. In the same time, we can notice that, okay, it's 1 minus something. So if you use the standard approximation, 1 minus something is exponentiation or in the power of this something. Then we can replace this formula by this one. So now let's say we still cannot, we don't know why the previous one converges, but like since it's approximation, maybe it's reasonable to study this algorithm. And that's what we are going, because this is actually appears to be a very well-known algorithm and a very prominent algorithm in convex optimization. So maybe we will have more hope to understand this algorithm instead of that one that is horribly non-convex and so on. So that's what we are going to do. Of course, here we have two, but since we have parameter alpha, we can just drop these two. It's not important. We can always like scale parameter alpha as we want. So this is our function f, and this is our update. And we want to understand everything what we can about this problem, about implicit bias, about convergence, etc. Okay, so the slide has a name. It's called like mirror descent. So let me explain what is mirror descent. So the gradient descent we already seen many times. And another way to think about is it's like we want to minimize our function f, but minimizing function f is difficult. So what we will do, we will minimize something simpler. We will use a first order approximation of our function f around the current point xt. And then, but it's a linear function, so we cannot linearize linear function, right? It will be just minus infinity. So we will add some regularizer, some quadratic regularizer. So it's an unconstrained problem. So if you just differentiate this function, right, to find optimality condition, you immediately see that you will get the standard formula for gradient descent, right? Because this is a linear, this is a quadratic, it's easy to minimize. And by minimizing, you obtain the standard update for gradient descent. Okay, so this is a good way to think about gradient descent. Again, as we did before, so now instead of this quadratic regularizer, let's consider more general regularizer. Let's consider like a Bregman distance as we had before. So it's the same formula as we've seen before. And now we will call this method either Bregman gradient descent, or more typically it's called mirror descent. So we just, it's the same formula, we just replace quadratic regularizer by a more general Bregman regularizer, or Bregman distance divergence, etc. So I hope it's clear. It's still convex and so on, under some, at least, like regularity assumption. Okay, so as before, if h is a quadratic function, then we will recover gradient descent. If h is entropy, then we will recover this algorithm. Notice that this is not the same entropy as before. Before, and this is important, before we consider entropy that was over unit simplex, now it's entropy over non-negative orthant. So each coordinate must be non-negative. It's like two different functions. And you could consider the over unit simplex, and it would be slightly different algorithm. And for this, you have this algorithm. It's actually pretty interesting that like just playing this plus infinity, you have a different kind of updates here. So the update here is, again, is clear. You need to solve this unconstrained minimization problem. You solve it and you obtain this update. So this is just very standard. Yes, questions?
And alpha is fixed all the time, or is it changeable during the algorithm?
That's a good question. So here because for update, it doesn't matter because it's just one iteration. I can use whatever I want, right? For derivation of one step. But in practice, of course, it depends. Very often it will be variable. So it's like an orthogonal question to this. For now, it's not important, but in practice, of course, it's very important, right? So because the larger step size you use, the faster you converge, but then you cannot use it arbitrarily large. So there is always like issue how to choose this parameter alpha. Yeah, usually it depends on the particular problem. For some problem, and of course, also it depends on the algorithm. For some problems, it must go to zero, converge. For some problem, it can be a constant, etc. For some problems, it can vary, and so on. Mm-hmm. Okay, so this is the algorithm. So basically, the algorithm that is approximation of that horrible thing is like well known. It's called mirror descent. If we consider entropy of a non-negative orthant. Okay. So let's understand why we have implicit bias for this algorithm. So this is our problem, and we denote by as the solution set. So this is the algorithm. If we basically take logarithm of this stuff, like element-wise, we obtain this update. So I wrote it in the standard notation of mirror descent. but basically gradient of h is logarithm, because if you remember, h was x log x. So if you differentiate it, it will be log x plus a constant. So we basically take logarithm from both sides and obtain this update. And of course, by telescoping this formula, we immediately see that basically gradient of h minus gradient of h at initial point will be in the range of A transpose, right? Because every this consecutive difference is in the range of A transpose. So we just sum up all of this. It's still range of A transpose. Now, so let's say we prove convergence of, it's still equation half to prove conversion, but let's say in the end we assume that we converge to a solution, right? So let's assume that we converge to solution X. So X solves our non-negative linear system, and let Z be this sparse L1 sparse solution. So it's also a solution of our system. Then X minus Z must belong to the kernel of A because they both solve linear systems. So the difference between them must be in the kernel. And because kernel and the range of A transpose, they are orthogonal to each other, we obtain this property. And this property tells us exactly, I don't want to derive it, but that's exactly what it means to be a projection. So let's think if h was quadratic function, then gradient of h is just identity, so it's just x minus x0. And in this case, it would be just a classical property to be of orthogonal. This gradient of h, it means x is a Bregman projection of x0 onto S. So this is just again the same generalization as we have seen. And now, if x0 is initialized very close to 0, to the origin, so eta has to be some large number, then we can show this the following bound. So basically L1 norm of x minus L1 norm of z is less, you remember that this is positive, right? Because z1 is a sparse solution, so x must be greater or equal. We have this bound, and so this is some constant, some lumbar function, some constant that depends on n, on e. Basically, it behaves like some constant divided over eta. So if eta is large, then this is is rather small. So which tells us that like, okay, it should be not far away from the sparsest norm. So that's basically one of the reasons why we observe this sparse solution. We can prove even more. Not prove, we can just show that our problem, I don't have time for this, but like it's possible to show that this problem is equivalent to some linear programming problem. And there are some conditions that guarantee even better convergence. So if you have some regularity assumption on the matrix A and B on the linear system, then we have even like linear convergence. So here it's not exactly correct formula because x, of course, it depends on eta, right? With different initialization, you converge to a different solution. So the larger eta, the sparser your solution is. And that's basically, it represents. So basically, you have exponential kind of here rate, right? The larger eta is, you will get pretty close to the sparser solution. So that's basically why mirror descent has this implicit bias. Again, we started this from the like non-convex problem, for the gradient for non-convex problem, and for that problem we still cannot answer why we observe the same implicit bias. We only said that okay, they are approximation of each other, and we know how convex problem has like why it has implicit bias, but we still don't know why non-convex problem has this implicit bias. So roughly speaking, it's very like the same, but we don't have a global result for this. Of course, in the neighborhood, it would be the same just because of approximation, but globally, we don't know. Okay, so that was one face of the coin, right? We understood the implicit bias of mirror descent for this particular problem. And another thing is to understand convergence, because here I said, like, if we converge, then we can talk about blah, 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 assumption stuff. But actually why we converge is, and like under which assumption on alpha will we converge is not clear. And it was actually not so trivial as appeared. And I think there are some works that study, again, this problem on the assumptions that alpha basically is infinitesimally small, but this is not very practical because it's like you will converge forever, and you would like to converge faster for this problem. Okay, so let's talk about convergence. So this is our problem. This is our algorithm. And usually, how people study convergence of mirror descent? There are two ways how you do it. This classical one is based on the strong convexity of function h. So means that this inequality should hold. The Bregman divergence, or in our case, it's like chi-L divergence. It has to be basically greater or equal than the quadratic kind of function. And in our case, it does not hold. And another alternative way is called relative smoothness. Again, it's not very important for you to know. There is another some inequality hold. Actually, because f is quadratic, in our case, it will be basically the same thing as before. So they both say, roughly speaking, the same. But they both cannot be applied, again, because we don't have a strong convexity. So we need to devise something more. Moreover, and it's very strange, right? Because this is like the simplest kind of function h. After quadratic functions, the entropy would be the next kind of thing to try. And the quadratic function is also, like, of course, the simplest function for optimization. And somehow, surprisingly, there was no result for this algorithm that worked reliably for large step alpha. Moreover, the problem is actually pretty bad. So in some sense, because it's like very unstable. So we could show that, like, if you take any matrix A, you fix any parameter alpha, the step size, then there will be always some bad vector B, so that the fixed point of this dynamical system are unstable. So, like, if you take any neighborhood of this point X, and you take there will be some initial point around this in this neighborhood that, like, without convergence. So which means that, like, somehow it's very strange, but somehow your alpha must depend on B as well. So usually B is like just a constant, right? It's a vector that is like only responsible for linear part, but somehow in order to find a good rule for alpha, we must take into account B. So the matrix A is not enough. And that's, like, not very typical in general for optimization. Okay, so basically the conclusion we can get from the previous slide is that we need to actually, we cannot use a constant step size alpha t. So that's basically the answer to Alexander Grigorievich's question. So we need to use some adaptive steps, some adaptive procedure to find step size alpha t. Also notice that our problem is very special. We kind of know that our linear system is consistent. So we know that we must, in the end, we must converge to f star. The minimum value must be 0. And when we know the minimum value of 0, a very popular way to use step sizes is called Pollak step size that has this formula. But again, in order to work with these step sizes, you must rely on strong convexity. You cannot, like, avoid this. Strong convexity is very important, and we don't have it. So we needed to kind of find out some other way to do it. Okay, so this is the algorithm. It's actually very similar to Pollak types idea. So we also have the same kind of thing. But we have some also strange kind of bounds here, 1.79, strange, right? Divided over something. So in a moment, I'm going to explain why, at least give a like big picture view why this algorithm works. So where it comes is the rule for step size alpha t. But notice that it's clear, of course, that it's kind of practical because it doesn't require any extra computation, right? If you know the gradient of xt, you also know the function value. You just substitute and you get some value f alpha t. You can prove that it's lower bounded by some stuff that depends on the matrix A, etc. And then you proceed. And for this step size, or for this algorithm, you can prove the following rate. So the best performance iterate would have the rate 1 over t, that is like expected for this kind of problems. Of course, you should get a sublinear rate because without strong convexity, you cannot get linear rate, of course. And this is some sublinear rate we get. Okay, any questions? So in the next slide, we are going to prove this result, or at least roughly speaking to prove. But for now, maybe you have questions. Okay. So
you have maximum 10 minutes, not more.
Yeah, I think I'm done in 5. So this is the algorithm. And let's consider what we are doing. So the first line, I understand that it may look a bit like puzzling, but this is just an alternative way of writing the first line. This is like 99% of optimization algorithms basically rely on this identity. In Euclidean case, it would be just a kind of the consequence of cosine law. If you have general setting with Bregman distance, we write the same thing. That is basically like you see, we have three terms that represent kind of the cosine law or like parallelogram law, etc., and like some extra term. So this is a very standard line, and like 99% of algorithms rely basically on this first line. So this is very standard. Since f is convex function, or not even convex, it's a quadratic function, we can use kind of this formula, right, by convexity, or here you can even just substitute because it's quadratic, not super important. So this is again very standard. Okay, now xt plus 1. If you substitute from the update of the algorithm, we get the following formula. And now basically the trick is that we have this horrible exponentiate function, and now we will use the standard bound, but upper bound for exponential, not the lower. And the reason why we have this 1.79 is because this standard inequality holds when like the parameter is less or equal than 1.79. It's not like rational number, it's irrational, of course, but we needed to stop somewhere, right? So we use 1.79. So we had this nice inequality then. Everything is eliminated, we can continue, and with just different notation, we wrote it as a quadratic norm with a weight of vector xt, like this. And now basically what we are doing is, okay, so we have something that depends on alpha t. We would like to make the right-hand side as small as possible. So basically we would like to minimize the right-hand side over alpha t. Just we are doing this in this way, but it's basically minimization. I just wanted to be rigorous because we have another inequality. So this is something something negative. This is something we would like to make it non-negative, and that's why we have this bound fxt divided by norm of this one. So this is the first term. So that's basically it, right? If alpha t is minimum of this one, we can just eliminate the stuff, and then we will telescope this inequality and get the rate, the one that we have in the previous slide. So that's basically at the end of the proof. And the rest is just technical details, so not super important. That's the main idea. Okay. Good. So very quickly, it's not super interesting, but like, let's say we studied from the general linear system, and half of the talk we only talk about non-negative linear system. But of course, it's very easy because we can just say that x is y minus z, when y is non-negative, z is non-negative, and we use like a column wise. We merge these two matrices by columns a and minus y, and basically now y and z are both non-negative, and again it's like a non-negative linear system, right? Because y and z, it just we have two vectors now instead of one. We can do the same things. The algorithm looks slightly more complicated, but the analysis is just the same because we can always treat by that y and z is the same variable x. So the formula is not important. It's just the same algorithm. The notation becomes horrible, but that's it. What other generalization we can do? So we still don't know the answer, right, for this non-convex kind of update. So because our mirror descent is just an approximation of this one, and we can only talk when alpha t is really small enough that they're close to each other. With large alpha t, we cannot actually say this. But what was interesting that like, so if you consider this algorithm, that is like that like each update basically majorizes this one. So our mirror descent update can be squeezed between these two updates. So for this algorithm, that is also very nonlinear, very non-convex, we can still do the same stuff as we did for mirror descent. So it's not necessarily about convexity. And it's, of course, again, it's very close to the first one, but for the second, we can say everything that we said before for mirror descent. And more general, here we were interested in particular problem, quadratic problem with entropy, but in general, we can study entropic mirror descent for any convex function f if you know f star, and the algorithm will work in the same way. Okay, I think it's all from my side. There are some references, and please ask me anything you want for now. Many thanks for your attention.
Thank you for very interesting and inspiring talk, I should say. And any questions, remarks? And what about the rate of convergence of the last algorithm?
Yeah, so the rate should be this one. So it's the sublinear rate, 1 over t.
Mm-hmm. Okay, any other questions? And concerning your own results, what is your contribution to this area?
So like the second part, what we did for mirror descent with this step sizes, it's our result with my PhD student.
Mm-hmm. And it is published?
On archive, yes, but not, it's under review.
Mm-hmm.
I have a question.
Oh, yes. Hello. Hello. Yes, please.
It's nice to see Yura.
Yes. Same.
And listen to a wonderful lecture about simple method. We started with the special connection with difference of square trick and mirror descent. It's wonderful. Question. Did you prove the theorem about Pollak step methods with results Pinsker inequality? No, you give brief of proof.
No.
Pinsker inequality.
But Pinsker inequality works over the unit simplex, right? So that's why you have strong convexity. Entropy is strongly convex over unit simplex. That's true. But over non-negative orton, it is not strongly convex because the domain is unbounded, right? So why Pinsker inequality is true, right? Because the Hessian is basically bounded, right? It's like it has lower bound. So if the domain is unbounded, the entropy is 1 over x. Hessian, it basically can be arbitrarily close to 0. So Pinsker inequality does not hold. But you're right that like the main idea of kind of proving the stuff was still type of Pinsker inequality. But inequality that depends on the iterate. So we did prove some type of Pinsker inequality. It was essential in the proof, but with a kind of adaptive, let's say, convexity parameter.
Thanks.
And this Pinsker inequality is about convex optimization. What is it about?
So it basically says that KL divergence is greater or equal than L1 square of L1 norm. So it's like KL divergence is greater or equal than total variation.
Okay. And I thought that sparse means that we have small number of coordinates different from 0.
That's exactly correct. That's why I put here like sparse in quotes, right? Is basically all the compressed sensing that it has appeared like 20 years ago was about like this particular problem, because people noticed first in practice that if you solve this problem, the minimizing L1 norm, magically you find a very sparse, like truly sparse solution. So which exactly in the sense that you said that like many zeros and a few non-zeros. It's not like 100%. You need to assume something about your matrix A to guarantee this. But in general, for good matrices, like but whatever it's like some random matrix and so on, this property calls automatically, and then you do recover the sparse solution. But it's not like truly sparse, it's still kind of sparse in this sense. So we recover this sparse solution, not like the sparsest one, not L0 norm, right? Because a truly sparse would be minimizing L0 norm, which is a hard problem. It's non-convex, like NP hard problem.
And we have a course of dimension. If you increase the dimension of X, what happens with your algorithms?
We have a course of dimension, but not in our case. I don't think we have any course. Nope. It's like first order optimization. Usually they're prone for course of dimension. It's like, of course, some constants will increase, but like in a normal way, there would be nothing like course of dimension. Let me see. What is the rate?
Accuracy of your methods, how does it depend on the dimension of X?
Yeah. So let's see how it will change. So the max of columns, okay, will remain the max of columns. The T will remain the T. Okay, the distance R will change, but again, it's a very controllable way, right? It's just like additively will change. So you have 1 plus 1 term more. So there is no course here. Of course, it will change, but very in a clean way, let's say. If you use some second order methods, for instance, right? Second order methods have this course of dimension because the larger your problem, you have maybe cubic dependence complexity. But here, everything is like analytically, every step is analytically computable. So there is nothing to worry about.
So you can work with a large, how it is called, when we have the larger the sample size, the larger the dimension of X.
Yes, I think so. I mean, of course, we are still bounded by the memory of the computer or whatever, or the how powerful the processor is. But in general, it's like there is no limitation.
Okay. Any other questions? And I sent a reference to the slides of this talk.
Yeah, my apology, because my slides are in HTML format, and it may not look exactly the same on your computer because it depends on the kind of format. So if you have a different kind of scale of width and height, it may look not the best way. So apologies for this, but I cannot make it in PDF, unfortunately.
Okay, then.
One question.
Yes, okay.
What you know about implicit bias for algorithm in saddle point problem, variation inequalities, or some equilibrium problems?
Actually, no, I don't.
Fixed point problems for some
nope.
Variation like Halpern,
yeah, I think you can say that like Halpern, but in some sense, Halpern is like, I actually don't like when people say that Halpern method has implicit bias, because it's like Halpern method is a modification of like Krasnoselski-Man, where you injected this kind of initial point, whatever is X0, and you converge to a projection. So somehow, it has this property, but for me, it's not like implicit, because you have this part that basically very explicitly like push you towards this point, right? So somehow there is not like here, at least when I learned about these properties of different algorithms, for me, it was always like surprising thing, something surprising. It was like unexpected. But for Halpern, it's like, okay, you expect this, right? Because this, in every update, you like push it further and further to this point. So it's not so implicit for me. But in some sense, yes, it's a similar property, of course. Yeah, so Halpern, yes, but it's more general, right? It can be for any fixed point.
And I can comment, in modern statistics, there is very interesting object. It is a so-called fractional Brownian motion. And I can refer to the book by Yulia Mishura on this matter. And it is very popular in financial mathematics nowadays. And for such processes and related processes, the key problem is how to estimate Hurst coefficient H. And it is done somehow by very tricky optimization. If you will be able to use your methods and improve the convergence, it will be publication of great value in this area. You can look at this monograph by Yulia Mishura and see the problem.
I need slightly better, more precise location. Like the monograph is like probably pretty complicated to find this.
No, I mean, it is quite. It is like a text.
Just enter exact reference to the chart.
Okay. Yeah. Thanks.
Okay. Then, if there are no further questions, then probably we will thank again the speaker. And he has two more very interesting topics for our seminar. I hope in autumn we will listen to your other topics on this matter.
Yeah. Thanks a lot. Thanks a lot for the invitation. It was really a pleasure to give a talk and like answering all the nice questions. And of course, like if you have some further questions, don't hesitate to send me an email. And especially it was nice to see some familiar faces. Yeah.
Okay, then thanks to everybody for coming, and we will finish our session for today.
Thanks a lot.
Yes.
Okay, goodbye.